last method for the determination of order of reaction, isolation method. This method is applicable for any complex reaction like this. On the system of many reactants, 2 reactants or 3 reactants. This is equation, general equation and the rate expression for this. As you know, X stands for the order of the reaction with respect to A, Y with respect to B. But it is not possible to find the values of X and Y simultaneously. You have to perform a separate experiment to find the value of X as well as to find the value of B. For that, we are using this technique. This is the most important one because it is the one applicable for most of the reactions. We are keeping very high concentration of B, that is comparatively to A. Concentration of A is very small, concentration of B is very high. If that is the case, the change in the concentration of B during the reaction is not appreciable. It is almost, what is that, almost appears, it almost appears constant B when the concentration of this is very high in the reacting system. Even though change is there, that is not an appreciable change. It appears as almost constant. That is why we are making some approximation. If the concentration of B is very high, then see the equation is reduced to this equation 1. This is already constant. When this constant into K is a constant, K dash. So rate of reaction is almost, what is that, is a function of concentration of A, equation 2. So using this equation, let us go for an experimental determination. As usual, we require a reacting system and additional equipments for the measurement of the concentration of reactant at different times. Monitor the concentration of the reactant. So in this system, this constant, because of very high concentration is constant, this becomes a variable. We need to monitor the concentration of A at different times, measure the values and tabulate them. This is a tabulation. Concentration of A versus T. And these values, you put them into graphical representation. As you know, this is the same graph. What is that? Graph for the variation of concentration of the reactant. It's the same graphic rate. From the graph, as you know, one can find out rates of reaction. Any two rates of reaction at any two concentration rates. For that, as usual, what is the previous case? Any 2 points and draw the tangent. Find the slope. Slope is tan theta. That is the rate of reaction and the concentration for this concentration. Rate of reaction for this concentration. So if you know the NO2, that is 2 rates for 2 different concentration, just look at the equation, what the equation applicable for this reacting system, this is the one. So for set of values, this equation becomes 2 equation like this, because same equation, and you can take the ratio because the reacting system is same. Ratio of this is for concentration rate. So reactant concentration corresponding rate, reactant concentration corresponding rate. These values are fixed. Take the ratio. So ratio means knowing this value, we can evaluate the value of X, taking log of both sides. X equals logarithm of this ratio, log of this ratio. This value is known, this value is there. Take the log, take the ratio of value of X. This is how the value of X can be evaluated. by applying this technique. What is the technique? Keeping very high concentration of one of the reactant, that is concentration B. So this is known as, we are isolating. Actually, by doing so, we are isolating the effect of concentration on the rate of reaction. That is keeping very high concentration. So this concentration will be isolated. That is isolated from the concentration effect is isolated on the rate of reaction. That is called isolation method. Now repeat the same experiment but reverse. That is keeping very high concentration of A and low concentration of B. The same reacting system with this difference. The same procedure you follow. Follow the same procedure as we did it here. So now when the system, that is when the concentration of A is very high comparatively to B, so this equation, what equation? Equation 1 takes the form. Rate of reaction, that is concentration of A is very high, it becomes constant. Constant into constant is a constant like this. Under this condition, the rate of the reaction is a function of the concentration of A only. So the variable and constant. Now the equipments with that instrumentation, let us measure what is that experimental values at different times. The concentration of B we are measuring. So concentration of B at different times. Here concentration of B at different times. And tabulate the values into the graph. From the graph, find the rates. Find any two rates at two different concentrations, like the one tangent and tangent. That is what the same way as we did in the previous case. That is the rate of reaction when the concentration of the reactant is B2. Rate of reaction, concentration of B, concentration of B is B1. That is the one here. Rate. So now the equation, we can write the equation for these two set of values. R2 is equal to K into this. So B2 rate, B1 rate, and take the ratio, same reaction. So this becomes like this. So same way I can calculate the value of Y. So value of Y is equal to logarithm of this divided by logarithm of this. The same calculation as we applied here. And Y, get the value of Y. So if we take X plus Y, sum these two. So what the value we have evaluated from this first one plus this value gives the N, order of the overall reaction. So this is how you can evaluate the value of N for any complex reaction or any reacting system more than one reactant. This is the most important one, isolation method.